Okay, hi. Let's finish up with chapter 3.1. Remember last time I said that it was a lot and I needed to kind of break it up a little bit. And so I'm going to finish up with 3.1. We're going to talk about 3.2. When we're done with this section, you'll be able to do the homework for both of those sections. Let's get started. Okay. So let's look at the domain of a function. I've mentioned it a couple of times in the last lecture, and it's a consistent theme throughout this entire course from this point forward. All the functions that we are going to study, and indeed, when you go on to pre-calculus and when you go on to calculus, your calculus sequence, it is going to be a concept that comes up all the time. You're almost always, when you are introduced to a new kind of function, going to be asked, what's the domain of the function? So let's go ahead and get that straight. So fortunately, it's really straightforward, okay? For all functions, does not matter what the function is. The craziest function you can think of, okay? Doesn't matter. There's only two situations that keeps a function from having the domain of all real numbers. In other words, there's only two situations that restrict what values you can actually put into a function, right? Just because you have a function doesn't mean every number from negative infinity to positive infinity can be evaluated at that function. Now, almost all of them can, and there's only two kinds that can't, and that are functions that are rational because you cannot divide by zero, and that are functions that are even rooted radicals, square roots, fourth roots, sixth roots, eighth roots, 88th roots, even radicals, rooted radicals, because those cannot have negative radicands. You cannot have negative numbers underneath them and produce a real number. Okay, so those are the only two things that jack up any function you can think of from not having the domain of all real numbers or not allowing any number as an input. Okay, now back when I was in college algebra, before you were born, for sure. I made up a little symbol that I drew so I could remember what they were. And I'm going to draw it for you. And the domain is all real numbers except, and this symbol here is called Blackboard Bold. It is also right here. And that stands for all real numbers. So that's every number you can think of except for imaginary numbers, okay? So all real numbers except, and the two things that mess it up is you cannot have a zero in the denominator, and you cannot have a negative under an even root. And I just put a square root because, oh, and that kind of ran together. I just put a square root right there because that's really what you'll mostly come in contact with, but that is included to the fourth roots in any even root whatsoever, okay? Now, how do we handle this first case? We handle this case by setting the denominator equal to zero. That becomes the numbers that the domain cannot have. And how we handle the radical is we set the guts, that's the stuff inside of the root, inside of the radical. The radicand is the guts, and we set that greater than or equal to zero. And if in the denominator, only greater than zero, because it can't be equal to zero in a denominator, okay? So these are the rules. This is what we're going to stick with. And now let's see what the domain is for these guys. Okay. All right. So again, I'll remind you that it's all real numbers except X can't be a zero in a denominator, and we can't have a negative number under a square root. Okay. So when we take a look at our first example here, f of x is equal to 7x over 3, we have this situation, right? We can't have that. So what do? We're going to set the denominator equal to 0 and find out what number messes it up. Okay, so we'll say x plus 3 is equal to 0, so x is equal to negative 3. Now, you don't have to draw a number line, and I'm only going to draw a number line a couple of times, and then we're going to be able to see this without a number line. But let me draw a little number line here. And this is infinity, and this is negative infinity, right? The biggest number in the whole wide world, the littlest number in the whole wide world. And I'm going to put negative 3 in here somewhere. Now, the domain, all real numbers is this number line from negative infinity to positive infinity. That's all real numbers, okay? So here we know it's all real numbers except whatever value makes the denominator 0. So this is bad. So that means that our solution comes from negative infinity up to negative 3, and then it picks up on the other side of negative 3, and it goes on to infinity. And we write our domain in interval notation. So our domain here is going to be from negative infinity to negative 3. It can't be equal to negative 3. Open union from negative 3 to infinity. Now, I know we've talked about the open parenthesis versus the bracket. And remember, the bracket is including, and the parenthesis is up to, but not including. Okay, and so to make my point here, for this side, negative infinity to negative 3, that means that negative 3.000000000000000000001 is in that piece in the domain, but negative 3 is not. So just as close as you can get to negative 3, but not negative 3. And then in this other set, from negative 3 to infinity, negative 2.999999999999999 as far out as you want to write is included in that part of the domain, but it is not included in the domain because at 3, that makes that bottom 0, and that makes that undefined. Okay? All right, so that's what the domain is. Let's look at the next one here. G of x is equal to x squared plus 1 over x plus 8. Now, anytime I see an equation, and it doesn't even matter if I've ever seen it before. If I'm asked to find what the domain is, there's two questions I want to ask. Is there a denominator? And is there a square root? So is there a variable in the denominator? And is there a square root? Those are the two questions you want to ask. Is there a variable in the denominator? And is there a radical, right? An even radical. but you want to pay attention if it's any radical. So let's just ask those two questions. So if you look here at G, there is no denominator that has a variable in it, right? 1/2 is just a number, it's just a constant. So there is no denominator and there is no radical. So for this guy, the domain is equal to all real numbers. So negative infinity to positive infinity, or you could write all real numbers, but I'm sure that your homework probably requires you to put it in an interval. Okay. Let's go to the next one. H of x is equal to 5x over x squared minus 25. Now, is there a variable in the denominator? Yes, there is. Is there a radical? No, there's not, but there's a variable in the denominator. So we need to set the denominator equal to 0 and solve it. Okay, now we could use the square root property here, or we could recognize that this is the difference in squares and just whip it out. This is x is equal to plus or minus 5, right? So that means that 5 is bad and negative 5 is bad. Let's just draw a picture of that real quick, just because I want to make sure everyone understands. So negative 5 is bad and 5 is bad. So we're actually going to have 3 sections, right? Because the only thing that's bad, it's not all the numbers between negative 5 and 5 that's bad. It's just negative 5 that's bad and 5 that's bad. All right, so from that picture, then we can just quickly write our domain. Remember, the domain is always the x values, and we always go from smallest to biggest. So starting from the left, it's in the direction that we read. So I really like reading domains off of graphs or whatever, because it's just in the direction that we read. So the smallest number is going to be negative infinity to negative 5. Parenthesis, because it can't be equal. Union, picking up again on just on the other side of negative 5 to 5. And then picking up again from 5 to infinity. Okay. All right, so let's throw a you do your way. Let's take a couple minutes because you're going to have to factor that denominator. Don't forget to factor out the common factor out of that denominator before you start using your AC method or whatever. So let's factor that first. We recognize that there's a variable in the denominator and there are no radicals. Give you a couple minutes here to factor this. If you're not factoring very efficiently yet, you really need to keep on practicing. If you need some extra problems to practice for factoring, just holler at me. I'll be sure to get you some problems to practice. Okay, so you should have pulled this 3 out because 3 is common between all of these, and we're setting this equal to 0. So we'll have x squared plus 2x minus 3 equals 0. Because these are multiplied to each other, that 3 can be divided out of both sides. So that just basically goes away. It's not consequential to the solution here. So now we have x squared plus 2x minus 3 equals 0, and that factors x plus 3, x minus 1 equals 0. So we have x is equal to negative 3 and x is equal to 1. So when we want to write the domain here, of course, we're going to start from the smallest to the biggest. And if you can just imagine looking over here at this number line, and we will replace this with negative 3 and with 1, we'll still get those 3 sections, and that's going to start at negative infinity to negative 3 union negative 3 to 1 union 1 to infinity. Okay. Let's do a couple more. I hadn't done any with radicals yet. And look, I have one that has radicals and a denominator. Yay! Okay, let's look at this one right here. Now, when we have radicals, what did I say? We set the guts because they can't be negative. The guts cannot be negative. So we're going to have to set the guts greater than or equal to 0. Okay, and then we'll solve this. So we get negative 3x is greater than or equal to negative 4. Divide both sides by negative 3. Don't forget, when you divide an inequality by a negative number, you flip that inequality sign. Okay, and now this predicts this is what the domain is. This says that x has to be less than or equal to 4/3. And since I'm drawing pictures tonight, I'll go ahead and draw this picture just to remind you, but we did do these inequalities in the first unit, but less than or equal to goes that direction. So our domain starts at negative infinity and goes to 4/3. And it's okay for the function to equal 0 here, so we have a hard bracket. And then finally, this last one, we have both situations. We have a denominator and a radical. So we need to handle both of these things separately. I'll handle the denominator first because usually those are a little bit more straightforward. So if I do the denominator here, we have x can is equal to negative 5, right? So we know that that's the bad number. We know x cannot equal negative 5. That's what we know. And then when we deal with this radical here, we have 3x plus 1 has to be greater than or equal to 0. It's okay if it's greater than or equal to 0 because 0 is an okay number. Anything over 0 is bad. Let me remind you again, if the 0 is over, it's 0, but if the 0 is under, it's undefined, right? So that's the bad. So let's go ahead and finish solving this. So if we subtract 1 from both sides, we have 3x greater than or equal to negative 1. X is greater than or equal to negative 1/3. Now we have to put these two ideas together. So I'm going to draw a picture. So we have negative 5. Oh, why did I write negative 5? That's not right. That's positive 5. Look at that. I caught my mistake. Hopefully you guys were yelling, she's making a mistake. but I caught it. So that is cool. Okay. Be sure to put your numbers on the number line in the correct order, right? And I'm going to graph x is greater than or equal to -1/3 first. Okay, so x is greater than or equal to -1/3 looks like this. And x cannot equal 5. So basically, we've got this area right here, and then this area right there. So let's get our domain. Starting from the furthest left, and it can be equal to -1/3 to 5. Can't be equal to 5. Union, other side of 5 to infinity. All right. Okay, let's move on from there. Now, the last topic from section 3.1, and now you can see why I cut it off and decided to move it to another lecture, is operations on functions. And this is pretty darn straightforward. When you add two functions together, you combine like terms and add them together. When you subtract them, you have to be mindful that you're subtracting the second function from the first, kind of how we had to be mindful when we were doing our average rate of change in the last section. And then the product is just multiplying them together, and the quotient is just putting F over G. It's the simplest one, in fact. Notice that G of X cannot be equal to 0. And I am going to ask you, usually, if I ask you for the quotient, we'll also ask for the domain. Right? Why would I ask? Because obviously there is going to be a definite denominator in that situation. And so domain is important. Okay, so I don't know why I wrote this here and then I put it here, but I did. So let's take a look at this example here. Actually, I think I know why, but anyway, okay, we'll use the space that we might need. All right, so let's take a look. Oh, I didn't show you. I didn't talk this through. So the sum and the difference means f plus g of x is equal to f of x plus g of x, and f minus g of x is equal to f of x minus g of x. This is a compound operator. And it kind of helps you from having to write a whole bunch of redundant stuff. And so you follow across the top, and that's what the sign for that rule is. And if you follow across the bottom, that's the sign for that rule from the bottom. Okay. And then we've got our product where you just multiply the two functions. And then, as I mentioned before, the quotient, which looks the scariest, but is actually the easiest, where you write one function on top of the other. No work really needs to usually happen with those. Okay, so let's take a look here. Let f of x, 1 over x plus 2, and g of x, x over x minus 1, and we're going to find all these operations. So the first one is the 2 added together. So I'm going to say 1 over x plus 2 plus 1 over x over x minus 1. I should have said and simplify. I'm sure you're going to have to give the simplest form on your homework. So what are we going to have to do? We're going to have to put together the LCD. And what is the LCD here? First denominator, write it down completely. We need an x plus 2 there. How about this guy? We don't have an x minus 1, so we'll need an x minus 1, right? Now, we're not solving these. These are expressions that we are simplifying. And so we are not multiplying through and getting rid of any fractions here. We're just making one big, pretty fraction that has a common denominator. So we're going to do like we've done before. We're going to multiply the x plus 2 by the fancy 1, which is x minus 1 over x minus 1. And we're going to multiply this right-hand side by the x plus 2 over x plus 2. Might not be able to record all of my things tonight because I'm starting to make silly mistakes because I'm tired. Okay, let's get this one done though. Put this in the books. All right. Now let's clean this up. So we're going to multiply through because we're just trying to make it one fraction. So 1 times x minus 1. So we get x minus 1 plus x times x is x squared. X times 2 is plus 2x. And that is now all over x minus 1, x plus 2. I did not leave at all enough room on this. So I'm just going to mark this out and we'll do it over there. And so as we keep on going here, then let's put this together. This is x squared plus 3x minus 1 over x minus 1, x plus 2. And so that's what f plus g of x is. Now, of course, there's going to be simpler things than this to do, but I thought I would go ahead and take the time to get a little bit of practice in and get you guys having some experience with some of these ugly irrational expressions that we need to put together. Same thing here with the f minus g. It's going to work the exact same way. We're going to need to multiply this guy by the x plus 2 over the x plus 2. I'm going to try to write a little bit smaller here. And this will be the x minus 1 over the x minus 1. Do this multiplication. So we'll have x minus 1 minus x squared minus 2x. Be real careful. That sign right there carries when we multiply those through, okay? That's a common mistake that people make, so be careful. X minus 1, x plus 2. And so that's going to give us, let's see here, negative x squared minus x minus 1 over x minus 1, x plus 2. Now, I'm not sure because I haven't looked at the homework yet. This could be simplified one more little step. I would take it as it stands, but if you have any trouble with your homework, it might be requiring it to be like this. I'm just not sure. I'm just trying to cover my rear end here. It could be this negative x squared plus x plus 1 over x minus 1, x plus 2. And that would be our f minus g of x. Again, this is tedious. Just so you know, clearly, chapter 3 is the tedious chapter. So far, it's been pretty tedious. Okay, let's keep on going. Let me do C real quick, and that was F times G of X. And that's going to be the F of X, 1 over X plus 2, times the G of X, which is X over X minus 1. And believe it or not, this is pretty straightforward because that's just going to be X over X plus 2 times X minus 1, because when you multiply, I got too close there. When you multiply two fractions together, it's shirts times shirts and pants times pants, right? You just multiply straight across. X plus 2, X minus 1. I just really like saying shirts times shirts over pants times pants, so that's why I have to say it all the time. You'll hear it more from me, I'm sure. Okay, there's the answer there. Can you cancel anything here? No, you cannot, because that X stands alone in the numerator, and on the bottom, the X is connected to the 2, so you can't separate those, or the X is connected to the -1, and you can't separate those. So this is the most simplified form. Let's finish off with the F divided by G. And so here we'll have 1 over X plus 2 divided by X over X minus 1. Well, this is pretty nice because it's already a fraction over a fraction, so we can change, flip, right? Keep the first one the same. Change division to multiplication and flip this guy over. So as we clean that up and we multiply shirts times shirts and pants times pants, X minus 1 over X times X plus 2. Now, personally, I prefer it in that method because in factored form, you can readily do anything with it. I could answer all sorts of questions about this right now as in this form. But again, I haven't looked at the homework and I'm not really sure what they're going to expect. So they might want it like this as well. So you could write it, I'm going to write or here. You could, so this is a stop and this is a stop, but just in case, again, if your homework gives you a hard time, you could write it like this as well. I'm not sure how they're going to expect. Okay. Awesome. Now let's move into section 3.2. Let me pause for just a second. I need some more water. Okay, thanks for the pause. Let's start here in section 3.2. And since it's a pause time, let's go ahead and get today's silly phrase for section 3.2. It is the mirror. The mirror is not on my side. The mirror is not on my side. Okay. Let me find where we are in my notes. Okay. All right. So here's some basic graphs. There's tons of basic graphs, but here's 4 basic graphs. Our first graph is y is equal to x squared. The second is y is equal to x cubed. The third is x is equal to y squared. And the fourth is a circle, x squared plus y squared equals 1. Let's take a look at this theorem. The theorem says a set of points on the Cartesian coordinate plane, or the xy plane, it's also called, is the graph of a function if and only if every vertical line crosses the graph at most once. In other words, If we draw a vertical line and it crosses the graph more than once, it's not a function. Sometimes it's easier to define something as what would make it not that than what makes it that. If not, we could be writing a million lines here. So the alternative here is if a vertical line crosses the graph more than once, it is not a function. So we can see here pretty quickly as we look across here that we can say this is, yes, this is a function. Even imaginarily, yes, this is a function, but this guy definitely is not a function. And this guy definitely is not a function. Okay, so if it crosses the graph, not the axes, but the graph that is drawn on there. Also, to be noted, when we're just looking at an equation, you can notice here that if there's a power on the y, that automatically disqualifies it from being a function. So let's move on to this crazy graph. This is actually a graph from trigonometry, which is why you're seeing the measurements in pi. And when you come on to pre-calculus, either in the summer or in the fall, next fall, we'll be dealing with a lot of pi's. So let's take a look at this first question here. We're going to read some details off of this graph. First, it says answer the following questions. The first question is find f of 0. So f of 0 is asking us to find what the value of y is, sorry, when x is 0. So when x is 0 right here, x is 0 right here, y is equal to 4. So f of 0 is equal to 4. I'm going to do the easy ones first. So f of 3 pi, and why are these easy? Because they're already marked on here. And here we can see I've labeled this point here, 3 pi and negative 4. So when f is equal to 3 pi, or f of 3 pi is negative 4. So when x is equal to 3 pi, y is negative 4. How about f of 3 pi over 2? Now you might be like, well, where in the heck is 3 pi over 2? She didn't give me any of those. And that's true because I wanted to talk about it. So only paying attention to the x values. I'm going to come up here and I'm going to write in our pi. And I'm going to come up here and I'm going to write in our 3 pi. Because once I write it in like this, usually it helps students see it. 2 pi. Okay. So if these are our values, 1 pi, 2 pi, 3 pi's, you can ignore the pi right now. It's just part of the number. But if this is 0 and this is pi, then that makes this pi over 2 or 1/2 pi. Right? Because between 0 and 1 is 1/2. So between 0 and pi is 1 pi half. Now, what happens between 1 and 2? Between 1 and 2, we have 3 halves, right? So between pi and 2 pi, we have 3 pi halves. And now we can kind of start seeing the pattern and counting it. 0, a half, 1, 3 halves, 2. Or let's do it this way. 1 half, 2 halves, 3 halves, 4 halves. So this would be 5 pi over 2. 3 pi is 6 halves pi, right? So 6 halves, and then this would be 7 pi halves, and then 4 pi is 8 pi halves. So that gives us all the rest of our numbers here. So f of 3 pi halves is 0. But we just had as a little lesson on how if I give you certain values in an interval, even if they're numbers you're not familiar with, you can figure out what the values are in between when you're looking at the middle values. Okay, let's take a look at the domain here. So what is the domain? Remember, the domain goes from the smallest x value to the biggest. And domains are x values, and you're going to kind of look this way from left to right. So the domain here is the smallest x value is 0, and it is a value, and the biggest value is 4 pi. Now the range also goes smallest to biggest, but the range goes from bottom to top because we're talking about the smallest y to the biggest y. And mind this, the range is the only kind of interval. The range is the only interval you use y values for. And I'm going to write this down, and you're going to forget this, but I'm going to write it down and make a big deal about it. The range is the only interval that uses y values. Spoiler alert, we're going to do other kind of intervals. So people often get confused and want to use y values. The only one you can use y values for is the range. Okay, so let's take a look. Starting from the bottom, right? I'm going to look from bottom top. The smallest y value here is -4. And go up to the last y value you see, or the tallest y value you see, and y, remember, is the second component here, and that is going to be +4. And now finally, we're going to ask for the intercepts. And remember, our x-intercepts happen when y is equal to 0, and our y-intercepts happen when x is equal to 0. And we can again read all this right off of our graph here. Our x-intercepts are pi over 2, 0, 3 pi over 2, 0, 5 pi over 2, 0, and 7 pi over 2, 0. And our y-intercept, there's only one y-intercept. There's many times multiple x-intercepts, but there's only ever one y-intercept. The y-intercept here is 0. and 4. Okay. Let's answer some more questions. You thought we were done with this. We're not done with this because you know that darn homework scrolls out a bazillion questions at you about a graph. So let's look here. How many times does y equals 2 cross the graph? So let's just draw in the line y equals 2. Here would be 2, so let's just draw a little. And now it says how many times does y equal 2 cross the graph? Looks like once, twice, 3 times, 4 times. Next, for what value does f of x equal -4? In other words, what x has y as -4? So we go and we look. Well, this guy's a -4, this guy's a -4. So x is equal to pi and 3 pi. Now the next one here says, for what value is f of x greater than 0? And what that asks for is positive y values. In fact, it's asking for the intervals of positive y values. And where are the y values positive and where are the y values negative? And these are all the positive y values, right? And we're going to write this as an interval. And because it's an interval, we have to use the x values. We want to say between what x's are the y's above the x-axis. Like literally that's oh, sorry about that. Hold on now, I gotta find my mouse and get it to scroll down there. Okay, so that's literally what we're asking. And so we look at where I have highlighted and we're going to look from left to right and we're going to list those x values just like we listed for the domain. And that's going to give us those intervals that those x values are going to produce values that are above the x-axis. All right, here we go. Ready? Uh-oh. I think uh, I've got a problem. Hold on, y'all. Don't know what happened, but I'm stuck. Where did why is this? Okay, I gotta pause. Let me figure out what's going on real quick. Sorry about that. Okay, I think I fixed it and then I messed it up again. Okay, and then I fixed it. Okay, here we are. Let's do it. All right, too tired for this. Last recording of the night. Okay, here we go. Starting from the furthest left, what is the smallest x value? It is and includes 0. Okay, now it's up to not including because it's right there on the line, right? So, in fact, yeah, so then where's our next value here? Remember, it was pi over 2. This guy was 3 pi over 2. We were at 5 pi over 2 and 7 pi over 2. And then this is 4 pi right here. Okay. So we're going from 0 to pi over 2. Union, picking up again, not at pi over 2, because from pi over 2 to 3 pi over 2, that's down here, that's negative. So picking up again at 3 pi over 2 to 5 pi over 2, and then picking up again at 7 pi over 2 and going to 4 pi included. And it's included because those are actually end points. I didn't make this point very obvious, but this one was. So those are actual endpoints, which is why those are included. All right, let's see where we are now. Oh, it's the last one. Are you as happy as I am? Okay, let's do it. Hopefully, I don't have to pause and I don't mess anything up. Let's finish this one up. Okay, let's consider this and answer a bunch of questions. Okay, so consider this rational function. This is actually a rational function just for the words here. Rational function means that there is a variable in the denominator. Okay, so this is a rational function. We're going to find the domain here. So real quickly, you can go, oh, it's got a denominator, x equals 2 equals 0. So x cannot equal -2. So our domain would be, if we imagine the number line with the only number marked out as -2, it would start from -infinity and it would go to -2. It would pick up again at the other side of -2 and it would go to infinity. The next question is the point 1, 1/2 on the graph of G? Now, how do we find that out? Well, we want to plug in the point and true statement confirms point on graph. Okay, so let's do that over here. I gotta get my stuff a little thicker here. It's hard to write that thin. Okay, so we want to know, is this the case? And we've got the point 1 and 1/2. Remember that this is the x guy and this is the g of x guy. So we want to know, is 1/2 equal to 1 plus 1? I do not want to fix that. So 1 plus 2. Right, we just plugged in 1 here and here. So is 1/2 equal to 2/3? Nope. And so we would say here no. And we could say 1/2 not equal to 2/3. If it asks for something, it's probably just a yes or no question. Okay, next question says, if x is equal to 2, what is g of 2? Write it in point form. Okay, well, g of 2, that's pretty straightforward. We're going to plug in 2 just like we plugged in 1 over there. So 2 plus 1 over 2 plus 2. G of 2 is 3/4. And if we write it as a point, we'll say when x is 2, G of 2 is 3/4. Next question says, if G of X is equal to 2, what is X? Now, to solve this, we're going to set the equation equal to 2. So let's do that over here. So we're going to say X plus 1 over X plus 2 is equal to 2. Now, because this is an equation different from the expression earlier that we put together, we're going to multiply both sides by the LCD to get rid of or kill off. We're going to kill off the fractions because it's an equation. If it's not an equation, you cannot kill off the fractions. You have to have an equal sign to be able to do it. So we're going to multiply both sides by the LCD, which is X plus 2. And we'll get X plus 1 is equal to 2X plus 4. Negative X is equal to 3. X is equal to negative 3. So, if G of X is equal to 2, what is X? X is equal to negative 3. How could we write that as a point just for giggles? That would be negative 3 and 2. That would be the solution point for that. And then finally, it asks us for the intercepts. And we know that we get the x-intercept when y is equal to 0, which is the same thing as saying when g of x is equal to 0. And we get our y-intercept when x is equal to 0. Okay, so let's do this x-intercept first. The x-intercept, let me scooch down just a little bit. The x-intercept happens when g of x is equal to 0. So I'm going to say x plus 1 over x plus 2 is equal to 0. Multiply through by the LCD. And when we do that, we get x plus 1 is equal to 0, right? Because the x plus 2's cancel here, and 0 times anything is 0. So x is equal to negative 1. And we like to write our intercepts as points, so it's concrete in our head on the fact that that is a place on the graph. And then our y-intercept here, that happens when x is equal to 0. So y is equal to 0 plus 1 over 0 plus 2. Y is equal to 1/2, and that point will be 0 and 1/2. Okay, awesome. We did it. Got the first two sections of chapter 3 done. And I will record the next one tomorrow after I've gotten some rest. You guys have a good night.